All right, 2.5 we were working on last time, and we had gotten to the point where we talked about the rule. So for those of you who haven't looked at this one, that's fine. This is the rule that we looked at. We take the derivative of whatever is the outside function, f prime, and we leave the inside remaining the same. And then we take the derivative of the inside function afterwards, and we multiply those. We've done two examples of that so far. The first example was very straightforward. We had seen a inside function that I circled in the red, and we did the derivative of the outside. We brought the 5 down, multiplied it by the 2. We rewrote the inside piece in red, and then we did a power 1 less. And then after that, we had to take the derivative of the inside, which was the negative 2x. So that first line there is exactly the actual derivative. That's the calculus part of what's going on. And then we did the same thing over here, except that we recognized that we could actually look at something that kind of started out looking like a quotient. And it's really not a quotient of two different functions unless you call one a function, which is just a little awkward. So we could actually write the denominator all the way up in the numerator with a negative exponent. Then it looks a lot like the very first example we did, and we can treat it very much the same way to do the derivative. And then we end up putting it back in the denominator. I did want to make one comment on this one. If we had done the quotient rule with this to start with, the quotient rule says we have the denominator squared, right? That's part of the quotient rule. And take a look at that denominator that you end up with in the answer. It's the denominator squared, right? So we actually would get the same thing if we did the quotient rule. It just would have looked a little bit different on the intermediate steps. Okay? All right, the next one's going to be much more complicated. Are you ready? Okay. This one has a square root in it. That's actually not the complicated part. The complicated part is that the part underneath the square root is a quotient. So the function that's inside of my chain is actually a quotient itself. So let's take a look at how that's going to be handled as we do this. So the first thing we're going to do is we're going to sort of think about this as being written as a power of 1/2. We've done that on multiple occasions now. So that's really nothing new. So when we take the derivative of this, it's still the part that's inside. This stays the same. That's still the inside function. It's just a more complicated inside function. So the part that's on the outside, that 1/2, we're going to actually use that to take the derivative of the outside. So what do we have to do with the 1/2? Bring it down as a multiplication factor. And then subtract 1 from it. So the inside will stay the same. I'm going to rewrite that piece. And so what will the exponent be then? It'll be negative 1/2. Good. So that's the derivative of the outside. However, the part that's circled in red, being the inside function, as we said, is a quotient, which means that now, as I do the derivative of the inside, I have to use a quotient rule. So I'm using the quotient rule in the middle of using the chain rule. Okay? And you're going to see a lot of that on the review that I gave you for the quiz on Tuesday. A lot of the functions where they're inside of something else and you have to use another rule. So let's use the quotient rule inside of this chain rule. So what do we do for the quotient rule? We haven't done that yet today. Right. Okay, so we rewrite the the denominator, and then we do the derivative of the numerator. So what's the derivative of the numerator? 6t, very good. And then I subtract, right? That's part of the quotient rule. And then what do I do? I write the numerator, very good. 3t squared minus 2. And I multiply by 2, the derivative of the denominator, which is 2. And all of this is written over the denominator squared. So the beautiful thing on Tuesday is that if you were asked this problem, you'd stop right there. The not so beautiful thing today, and as you're working on your homework, is you are going to clean this up and simplify it. The nice thing about it is that your answer is actually going to look much more concise, because this as an answer is very ugly, right? So we can simplify quite a bit. Let me sort of remind you a couple of facts about exponents. And you know some of this because we've been working with it. This exponent right here in the middle being the negative 1/2 means that I could take the fraction inside and flip it upside down and make it a positive half. Do you You guys remember that negative exponents actually make reciprocals of fractions? So that's one thing I'm going to do. The other thing I'm going to do is I'm actually going to take that power that's now going to be a 1/2, and I'm going to apply it to the numerator and the denominator separately. Are you guys with me? Okay, so that's what I'm going to do on the first piece. I'm going to rewrite this. The 1/2 will stay in front, and I'm going to write this as 2t to the plus 3 rather, to the 1/2 over 3t squared minus 2 to the 1/2. So I did two things at the same time. I flipped the fraction, and I sort of distributed, if you will, the exponent to each of the numerator and denominator separately. This is going to run into everything. Let's try this. Excuse me. All right, the next thing we're going to do is we're going to take that numerator on the second fraction, the quotient rule part, and we're going to simplify that. So as we simplify that, we're going to have another fraction here. I'll just use the multiplication symbol. I have the 2t plus 3 down here in the denominator, squared. What do I have this numerator going to be? Going to distribute, right? Okay, so the 6t is going to be times the 2t, which is going to give me a 12t squared. Plus 18t. And then plus 4. That's right. All right, so we have this numerator all distributed out anyway, and then we could actually combine a couple of those terms in the numerator, right? Which of them can be combined? Right, the ones that are squared, right? So I have still the 1/2 at the beginning. I'm going to do one other thing right now, just because it's a good time to observe this. I only have a limited amount of screen space. If we did this in multiple steps in your paper, that'd be fine. But notice this 2t plus 3 here, and this 2t plus 3 down here. We're going to be able to combine those. So although right now it's in the numerator with a positive 1/2 power, I'm going to go ahead and pull it back to the denominator and make it a negative 1/2 power, just so that they look like they're combined together on the same part of the fraction. You don't have to do that, but I think it's easier to remember the exponent rules with them both in the same location. So I'm going to write it that way, and then we can combine them in the next step. So I've got the original 3t squared minus 2 that's already in the denominator right now, and then I'm going to write the 2t plus 3 to the negative 1/2 down there. And then I also have this 2t plus 3 to the power of 2 that's down there from the other fraction over here. And then my numerator is 6t squared, very good, plus 18t, and then plus 4, right, Ben? Yeah. Okay. So like we said, we can actually combine this one and this. All right, so how will those two that are underlined in green combine? Right. Why will it be a power of 3 halves, Ben? Right, so we've actually got two values that are the same raised to different powers, and so we're going to add the powers together. One of the powers is a negative 1/2. The other power is a positive 4 halves. So when we add this together, we get a 3 halves power. So we have the same 3t squared minus 2t, minus 2 to the 1/2. And then now we have a 2t plus 3 to a 3 halves. There is exactly one more simplification we can do. Do you see it? Yeah, there's a 1/2 out here in front. It's this 2 in the denominator. And I actually have everything on the top that's even, so I can reduce those, and I'll divide each one of those by a power or by a factor of 2. So I'm going to get 3t squared, 9t, and 2. And after a lot of work, actually, on this one, we are finally done. It still isn't beautiful, right? But it's actually a lot better than the very first line we had in certain terms of being consolidated or simplified down into what it's got, into its individual factors. Any questions on this one before you go to the next one? Okay. This one asks us to find the second derivative of the function. We've done this in a couple of different times now. So what does it mean to find the second derivative? To do it twice. Yeah, a couple of you are saying the same thing, to do it twice. So what is the first step on doing this particular function? It is a chain rule because we should be recognizing that I can write this to a power of 1/2, right? So we have something that is the x squared plus the 4 inside of a power of 1/2. So we do have a chain rule. All right, so using the chain rule, somebody tell me what you get. Mm-hmm. Good. Now taking a look at this, we can do one simplification before we go on. I mean, we don't need to put that 1/2 back in the denominator because we're just going to take another derivative, right? And it's helpful as it is actually for it to be written in this form. It's actually pretty good. The only thing that we can really do that helps us to simplify is the 2's. And although I won't need it here, I'm going to go ahead and write the x at the beginning. If you write it at the end, it's okay. I'm going to go ahead and write it that way. I like seeing the power at the end for some reason. But something else has now happened as I go into my second derivative. There's a product here. Do you guys see it? I have this x, whether I left it at the beginning or at the end, and it's being multiplied by the part that's got the chain rule in it. So I have this function, and I have to use the product rule. That's actually the overarching rule that I'm using. But in the middle of using the product rule, I'm going to have to use the chain rule, because one of those functions that's underlined, namely the second one on my screen, is a chain. So it's going to have to use the chain rule when I do take its individual derivative. Okay, so we haven't done a product rule yet today. Product rule, what do I do for my product rule? So this is the second derivative I'm starting on. Yeah, and actually when I did it, then I actually presented it the other way just because I like to be able to write the first piece down, but what you're suggesting will work as well. I'm going to keep going with the right direction that I had, which means the first thing I'm going to do is I'm going to write the first one down. And then I'm going to take the derivative of the second one. And that's where the chain rule comes into play. So I'm actually going to get rid of the hard derivative at the beginning. So the derivative right here of this piece, right, of the piece that's underlined in green at this point, that one's going to be the chain rule. So taking a look at that second piece, what will the chain rule look like for that?
-1/2 times x squared plus 4 raised to the -3/2 times 2x.
That's perfect, Blaine. Is everybody good with those pieces? Any question about where anything came from?
Why do you have to do the chain rule with it?
The part that's underlined, in fact, I've got two parts underlined in green, so let me box that in. This part right here that's boxed in green, it'll show up pretty soon. This part that's boxed in green is a chain. It's got a piece of it inside of something else. It's got a function inside of something else. Anytime you're trying to take the derivative of something that looks like a chain, you're going to use a chain rule. So we've got the piece inside that gets rewritten, and then we've got this 1/2 that comes down with a new power, and then we're going to have the derivative of the inside. So even if it's sandwiched in the middle of a quotient rule or sandwiched in the middle of a product rule, we can still end up having to do a chain rule if there is a chain or a composite. It's actually a composite function is what it is. If there is a composite function present, and there is in this one. Okay? All right. We're not done. This is only half of a product rule because a product rule has an addition piece, and then we have the other way around. So this is the actual the direction that Ben was going to go to start with. So we had the original one rewritten, and then we did the derivative of the second one. Now we're going to have the first derivative, the derivative of the first piece, which is going to be 1 times the original of the piece that's boxed in green now. So I just rewrite that piece with no calculus involved on that part. All right, so let's just say for a moment that on your quiz on Monday, or Tuesday rather, I keep saying Monday, your quiz on Tuesday, that the part that I've just lined in red was where your function actually started. Like I gave you that and I said find the derivative, right? Because I could give you a function like that and then say find the derivative. If I did that, then the line right here where I've gotten to, that would be the derivative and you would stop, okay? But we're working with these problems in homework. We are going to simplify and get the final answer to a more concise form. So that's where we are now. I have lots of exponents that are negative, don't I? So I'm going to definitely pull those back down to the denominator. And I also have a little bit of cleanup I can do. There's a 2 here and a 2 here that would reduce. And then I have an x at the beginning and an x that was grouped with that 2x, so I've got an x squared. And I have a negative from the middle term. So I think all of that combines to negative x squared, right? Here's the negative right here. I have the x at the beginning, and I have the x with the 2x. So there's negative x squared. And then in the denominator, I'm going to have the piece that says x squared plus 4 to the negative 3 halves, which will now be positive 3 halves. The other piece of my function is much easier to write. It's just 1 over the x squared plus 4 to the 1/2. We're not done. What do you think we are going to do? What's that? No, we don't need any more chain rules. We're done with the calculus. We're absolutely done with calculus. We're going to add the fractions by getting common denominators. There we go. Good. So we've got to somehow combine these fractions into one fraction. And we don't always do that. I mean, I recognize that. But these two can be done that with quite easily because the x squared plus 4's match. Do you guys see that? That's why we're going to combine them. We don't just randomly always decide to combine fractions. It's just that these two fractions already have a fair bit in common, and so combining them into a single fraction is a reasonable step to do. Notice this has a power of 3 halves, and this has a power of 1/2. What is 3 halves as a mixed number? 1.5 or 1.5, right? So this is 1.5, and this is a power of half. So I just need another power of 1 of these to make it 1.5. So I'm actually going to be able to take that second fraction and simply multiply by x squared plus 4. Because the reality is that that's x squared plus 4 to the 1 plus this half, which is 1.5. Do you guys see that okay? I think it actually makes a lot of sense with the mixed numbers sort of perspective instead of the fractional, the improper fraction. 3 halves is the same as 1.5, so here's the half and here's the 1. All right, so I'm just about out of space. Let me move mine over here to the left a little bit. That wasn't what I wanted. Let's try that again. I'm trying to move just to, you know what, let's do it this way. There are drawbacks to not using a marker board. I don't have as much space, you know, I tell you what. All right, but on the bottom here, everything's going to move here in just a second for you, in theory. All right, so the denominators now match, right? They are both x squared plus 4 to the 3 halves. Take a look at those numerators, though. Some of you have already done this, I can tell. This is a negative x squared. Here's a positive x squared. And here's a 4.
Dr. Haynes.
Yes, did I make a mistake?
Considering since you both denominators have the power of 3 halves, would it not be 2x squared plus 4 to the 3 halves since there's 1 of each?
No, because think about what happens when we do fractions and we get them to have the same denominator. If I had 1/4 and I had 1/2 and we multiplied each of these by 2, the denominator stays the same, right? then that's what happens. We talk about it, I talk about this with my students who are training to do teaching for elementary school. What you want to remember is that when you're talking about denominators, think about something like a pie. When I'm looking at a piece of a pie, if I had a 1/4 of it and I had a 1/2 of it, when I'm done, it still is 4 pieces, so the denominator doesn't change. So once we get the denominators to match, we simply add the numerators together. Okay? It's harder to see when I'm working with variables, but with numbers, it's a little bit more concrete. What's my numerator going to be?
4.
It is. It's going to be 4. And actually, this is y double prime. Actually, on this one as well, that part that I just squared in right here, that's a lot simpler than where we were, isn't it? You know, the last problem still ended up looking kind of like a mess at the end, right? I mean, so that's a possibility. But it's also a possibility that when you simplify the denominator and the numerator, when you combine the fractions, that it actually ends up looking really good when you're done. And that's what happened on this particular one. Any questions on that one? Okay, we have one last example in this section. This example should look so different than the rest of it to you. Does it look so different? Well, it looks so different.
We're not given the beginning equation.
Yeah, we're not actually given an equation for any of these functions, right? We're just sort of given the names of the functions. And this one really this problem really tries to get at the conceptual understanding of what this rule says. So this right here is our function. It's supposed to be h of x equals f of g of x. And it wants me to find h prime of x. Well, actually, it wants me to find h prime of 1, but we'll do the 1 at the end. First, I need to start with what is h prime of x. All right, so we have a rule. I mean, that was what was back on the early part of the slides, right? It was the very first thing on your notes. What in the world is h prime of x when it's a composite function f composed g?
Shouldn't it be 1?
Go ahead, carry in. Let's do one. I know everybody's talking now, so carry in. Go ahead. What do you have?
F prime of g of x times g prime of x.
Right. Okay, that's what you guys are all trying to say in conglomerate, right? This is the rule that you have at the very top of your note sheet. That's the standard rule. So what we're actually trying to find now is we're trying to find h prime of 1. So I'm going to come in here and I'm going to replace every x with the number 1. Now parts of this we already have. I mean, I don't have anything up here that says f prime of g, right? But I do have something that tells me what g of 1 is. And I do have something that tells me what g prime of 1 is. So I can actually use the information given at the very top to evaluate those pieces. We'll do them in order. What is g of 1?
2.
It's 2. It's written right here, correct? G of 1, right there in the middle of the top row. And then what in the world is g prime of 1? Negative 2. That's the first thing on the second line. Do be careful. This does not say that I'm going to take 2 times negative 2, right? This notation still is combined as one feature. This is f of 2. So what is f of 2?
Would it not be f prime of 2?
Oh, I left the prime off in the midst of all the chaos of the technology. Yes. What is f prime of 2? Thank you, Blaine. It's what? It's 3, and that's the piece over here, right? Yep, so this is 3. This piece is still negative 2. So 3 times negative 2 is negative 6. So all this is an application of the process itself in general without function notation, without the equation notation, right? And I think you've got one of these on your homework like this. Any questions on this one? All right.